So we are going to talk about robotics, in particular path planning with robots. So currently, I think there is a tendency to think robotics is more engineering than computer science, but there's a lot that we do as computer scientists about how the intelligence builds. There's a lot of things around learning systems built for robots, and it gives us a really nice playground because the problems are much more difficult, I think, when you think about just data sets or things that are built in simulations, because the world is noisy, the world is uncertain, and there is a lot of things that we don't understand how the robots should work.
The problem is finding the end point, is it?
Finding a goal, yeah. That's the problem of a mobile robot anyway. It tries to...
Or does it have the goal and it's how it gets there is the question?
How it gets there is the question. So we do have, I think, situations where we need to decide where the goal is. And I think that is maybe earlier in the cycle where you decide on where to go. And then there's the problem of how you would go there without colliding into something or without disturbing anyone who's around. So we could talk about the sense, plan, act cycle again. So we had in the earlier video talked about it. And we typically talk about sensing, then planning and acting. In the sensing, you basically talk about getting the raw data from the environment. The robots have sensors and they look at the world to capture some form of raw data. There is perception here, which I think kind of lies in between sensing and planning. Sometimes
we're sort of like working out, making sense of
yes.
What the sensors have told you.
Yeah. So you may think of perception as part of sensing as well, depending on your perspective. So perceiving is about making sense of what you see, that raw data, and it can be focusing on different problems, such as what are the objects around me, but also where am I, so the localization problem, where do I want to go, and what am I in, for example, the mapping problem, what is the representation of this world that I am, which we haven't talked about a lot, but we do, in the algorithms that we will discuss today, we do assume that there is a map of the environment, then we choose to discretize it. So the planning here is the part that we are going to talk about. We are given a starting point, which is hopefully where the robot is at the moment, and a goal position, and you want to sort out how you go there most effectively. And then the acting part is how you actuate your motors and how you actuate that path.
I'm presuming there's a kind of looping situation here where you keep continually checking, right?
Yes, exactly. So basically the robot deals with the physical world through sensing, and the actions change the physical world. So all of this is actually a cycle, a pipeline, where you use information from the preceding blocks. Okay, so let's assume we have a map. I haven't shown you a map, so I don't know if I should show you one, and then maybe demonstrate what the robot could do in a simulated environment.
Let's do that, yeah.
Okay. So I have kicked off a ROS launch file.
So ROS is the robot
operating system. So this is the middleware we tend to use for programming most of our robots.
So on the right we're seeing the reality of the simulation, and on the left we're seeing the robot's perception.
Yes, it's the robot's perspective, exactly. This is something I use in my teaching. So this is a ready-made environment for the turtlebots that we also use in our teaching, and this is a tiny simulated turtlebot over here.
In the little box.
Yeah, that is our robot here in this large environment. The environment has a lot of rooms and some obstacles around. If we look at these files, actually I have created a map for you. And this is the map that the robot would be given. So it is what we call an occupancy grid. And it shows you what are the free areas, which are the white areas here, and the obstacle areas, which are the black areas. And there's some unknown areas where we don't actually, we haven't gone to, we don't know what it is. So that map is added to this visualization tool. So this is called RViz. And this is actually showing where the robot is in a slightly shifted way. So the robot is kind of lost, but not too much. And I can use this tool to give it a goal. So this is using the ROS navigation stack to compute a goal. So currently, it's not able to compute any paths, I think because the robot is seemingly on an obstacle, on a wall. But I can, oh, actually it did. Yeah.
So what's going on with the purple and the red there? Is that its perception of what's nearby?
So the purple red areas are what we call cost maps. So the robot is actually creating certain costs on the grid, and those are defining the no-go zones. They are also around the robot because we inflate the robotic structure so that it becomes free to move around obstacles. And it is slightly off here because it did think that it was at a different place. And as you can see, the robot in reality, in its own world, thinks that it is in the middle of the room, but in fact, it's a little bit shifted.
Okay.
So I can give it a better position estimate, which would hopefully clear this up, and I can clear all the costs on the map so that it's a little bit more clean. And these green things around the robot are particles. So we are running a particle filter in the background to localize the robot. So if I give it another goal, I think you covered it in the SLAM video, the robot, through looking at what's happening around it, would converge to a better localization. And it does still have this artificial cost map because it has no way to actually forget something that it has seen. So from its own perspective, it thinks there are obstacles
so that's
around there.
those kind of shadows on the outside.
Yes,
Right,
yes.
okay.
So it is an artifact of the mislocalization at the beginning. But now it is really nicely localized. So here what I do is the robot, we know where the robot is, and it is pretty accurate. And I can give it a goal like this. So this is a position and an orientation. And the robot would compute a path, which is about the planning problem we will be talking about today. So this one is actually using an A-star algorithm,
Okay.
which we also covered many years ago. So we will also talk about that.
What it will do is prioritize nodes that are going roughly in the right direction.
That kind of demonstrates the problem. And as we talked about, there is a map in that demo. So let's assume we have a map. And in our purposes, the map is a rectangle, empty. The goal is from a start position, start pose, to go to a goal. And what we are interested in robotics at least, is to move a body through the start configuration, this goal configuration. So what we are interested in are typically X, Y, theta, which is the position of the mobile robot because it is not flying, and the rotation.
So this is a 2D, obviously, in this
Yes.
instance. Yeah.
So for you can extend it. So path planning ideas, they can all be extended. And the second part, what we are going to discuss, will be mostly about the challenges of these algorithms when you go on to higher degrees of freedom, such as manipulators, and why we require maybe different algorithms for planning. So for the purposes of this video, I will be talking only about the XY, but this holds for higher dimensions. And the aim of path planning is, because I have a lot of colors, to find this path, which is allowing me to navigate from a start and a goal, a start position to a start pose to a goal pose.
Yep.
And for this very simple example, this is actually quite easy. This is even analytical, isn't it? There is a mathematical function which I can define because I know these positions in 2D, and this is the function that would lead me to it. Why we are not doing it in robotics is because the world is typically more complex. And also maybe another concept we should mention is motion planning. So dealing with robotics, you would sometimes hear the term motion planning and path planning. And while it's not
Is
defined...
that because you can't move in every particular direction? You have to take
Yes.
into account how your wheels turn.
Yes, that is one aspect. There is not a clear-cut definition between motion and path planning, but motion planning is about also how you're moving through this path. For example, if there are velocity constraints, rotational constraints, etc. Path planning is more focused on how you are geometrically moving on this. So that is our problem. So if the so maybe I do draw the scene again. If the goal is to move from start to goal, and if I can't actually have an analytical solution, I'll do pink. What I can do is to make use of graph-based algorithms. And path planning is very computer science. And in fact, most of the path planning algorithms are proposed by computer scientists for roboticists. So if we don't have an analytical solution, if we want to numerically solve it through graph-based methods, what we can do is we can populate this area with nodes, right? What can I do? Initially, the first thing that comes in your mind could be just I randomly put a node in places. So I put a node on my starting point, and then I randomly select a place and put a node over there. So the cost to go to this node is 0. And let's say this is 10 maybe. The distance, the cost of traversing this path, and the cost to go to this node from this to here would be 10. I could continue this process, such as I can have something here, and then I could find the closest node, and I would draw an edge in between them. Let's say the cost of this trajectory is 1, so this could be 1. Then I could maybe have something like this, 2 here, and the cost would be 3, and another 2 here, and then the cost would be 5 to go to this node from here. And now we can see, actually these are not that far away. So if I had a path in between these, the cost instead of 10 would be 6 to go to this node, which means that I actually cancel out this edge. Don't go this way in order to reach this node, go this way. And you can have paths that are not really very useful, taking you maybe to the other directions, and they can populate your graph. Adding more and more nodes, let's say this is 2, so this is 7, and if you get closer to the goal, you could add maybe not overlapping with it, but add a node around the goal, and you could assume that within a threshold you have achieved your job. So cost of going here would be 8. And this is not really optimal. You could possibly have something better if you had selected a node here, which would be 1 and 1 maybe. So the cost to go here is 1. So this should be updated to 2. This should be updated to 4. This should be updated to 6 and 7. So this is closer to being an optimal solution.
That's all right. So how long do you spend adding nodes until you stop?
Exactly. So this is not the best idea that you randomly add things. Like I could just play around here, right? I could add things, and then the graph would circle on itself, and I would be losing a lot of time. So that is not the best idea. A better idea is obviously something that we all know, A*. A* makes use of heuristics. So typically it works on a grid-based representation in the robot world. That's why we talk about grid maps. So the maps that we create, we don't use a continuous representation, but we discretize it. We select a grid size, we select a resolution for it, we lose some information over there, and we say this will be the space, the state space that my algorithm will operate on. So assuming that this is my start, and this is my goal, A* basically tries to put nodes into these grid cells and select a path that is moving toward the goal. So in general, such a discretization also limits your action space. And for illustration purposes, we assume that the robot can go sideways, up and down, and diagonally, and we assign costs over there. So because this is like 1, 1, 1, 1, the cost going to these cells would be 1, and this would be the square root of 2, so something like 1.4. But people demonstrate it as 10 and 14, typically, so that you would have a decent way of showing how you choose which node to expand. And the whole point of A* is choosing which node we are going to, because a different, maybe more naive expansion algorithm would go in breadth, like the Dijkstra, for example. It will expand the node and going in ways that...
find out everything when you don't need to know everything.
You don't need to, because we know that the goal is here. So what I know also is that I should probably move in that direction. So yeah, possibly the best way to go to this goal from this one is to go diagonally and then move this way. And what A* does is it computes 3 costs in doing so. One is the cost that has already incurred. So I have taken this path. So this is the what we call a G cost, 14. And there is a H cost, the heuristic cost, which is the distance or the cost that I have to incur in order to reach the goal. And this second H cost is always underestimating the reality. So you could have something like an Euclidean distance or something real, but you shouldn't overestimate the cost so that your algorithm is admissible. So in here, in this sense, I think we go 3 diagonal, 1 sideways, which means that our heuristic cost is 52, if I compute it correctly for this one, which makes the cost for this cell, the sum of these costs, which I will call the F cost, which would be 66. Okay? And for this one, it is similar. So I would go probably diagonally and 2 sideways. So the cost that I have incurred until now is 10. And what I have to do is 62, which makes the total cost here 72. So clearly at this moment, this one is a better choice. And for this one, we have to go maybe diagonally all the way. So it is 14 times 4. So 10 is the G cost, and 14 times 4, 56? Yes? Is it 56?
Yeah.
Okay.
Yeah, it's all right.
Then it is 66. Then you have to make a decision between these two.
Fine.
So what we are doing is we are actually filling all these cells which are adjacent to it, and then going to cells which has the minimum F cost at every stage. And it will hopefully lead me through a direct path in a much quicker way, because I choose to not expand these ones. So I'm kind of making my tree expand in that direction. Hopefully the maths is good.
Close enough. Close enough.
We lost that ability.
It's all good.
Okay, so that is the A* algorithm. And that is actually what is used in the simulation that you have seen. It is a very, very good algorithm. And it does work when you have obstacles around. And in here, if we had an obstacle, it would have probably found out different ways eventually. Maybe it would go this way and then choose these things. So probably this is a shorter path from this. So even though this looks better, or this looks better, after a few steps it should find this. Because A* algorithm would give you the optimal solution with the restriction of your resolution. So it will work.
Only on the grid.
Yeah, because in a fine grid you would get a solution that is more closer to the optimal solution. If I have such a coarse grid, obviously it is not the real optimal, but it is an approximation.
Yeah.
But presumably that's a trade-off against how much time you have to compute.
Yeah.
And,
Yeah. So those are all about representation and your choices. That brings us to the issue of whether this algorithm is usable at all times. So we had a very small grid here. Imagine I have a grid of 100 by 100, which gives me 10 to the power of 4 for the number of nodes that I have in this graph. If I had a three-dimensional space, so if my robot would swim or it would fly, then I would have 100 times 100 times 100 for the same grid size, which makes the complexity of my algorithm 10 to the power of 6. What happens if I have a manipulator arm, which has 6 degrees of freedom, 6 joints that I can control? Then it would be 100 times 100 times 100 times 100 times.
Every degree of...
Yeah, it would give you something like 10 to the power of 12 for your grid size, because you have 100 dimensions for each degree of freedom, and you have 6 of them, so 10 to the power of 12, which makes it like exponentially grow in the number of nodes that you have to deal with, which makes your algorithm less effective.
But there must be some tricks that you get to basically cull some of those or bring it down, that number, yeah.
So what we do when we tend to deal with manipulators is actually at the algorithmic level. So we said at the beginning it's not a very good idea to randomly select these nodes, but maybe it is if the, if the resolution is really still fine. Or if something like, even if we are in this zone and instead of this we really create a very fine grid, then your dimension is also increasing. So maybe we should do something random. And that brings us to the rapidly exploring random trees algorithm.
Okay.
So that algorithm does select nodes randomly, hence the name random, but it does it in a intelligent way.
So semi-random.
Yeah, you constrain it a little bit. So you try to go towards
Randomly in the right direction.
randomly in the right direction and not really making the edges too long, too far away. So it's not completely random in this space that's like in this.
So constraining it to your proximity in some way.
Yes. So instead of like selecting a node just here, select something around it, so you could expand in the locality of your current node. So you do expand the tree in a wiser way. And it is actually a, I think, simple algorithm. The implementation is very short. Again, we think that this is the starting configuration, and this is the goal configuration. And we assume that we have obstacles around, right? So let's say I have these maybe obstacles around me. Let's say there's something on the top. I don't know, something here. So we do have a space that we have to navigate in between. So you have to find a path instead of drawing something really linear. So what happens here is you choose a node randomly. So you assume your node is, actually I do have some props. Let's say you choose a node just here, which would be normally connected by a line from the starting node, because we do have a node here. There's no node here yet because we haven't seen it, but this is far, far away. So what we do is we select a distance and we project this node to fall onto that distance. So we move it closer to this, and then we draw an edge. And this is my node around. And then you do it from this node. So you put something here, this is far away, so you project it to be within the maximum distance. And then your tree becomes closer. So let's say if I had another obstacle here, and I choose something like this, and the projection actually falls onto the obstacle, I basically ignore it. I don't add it to the graph because there's no way I can traverse to this. So the validity checks could be also pretty simple because you do still have a known map. So what this algorithm would do would be expanding the search tree, and sometimes in directions that are in the opposite way, but this doesn't really matter because those won't be used, and ultimately reaching a target. So if you put something here, so if you get close enough, you say this is okay. And this is rapidly expanding. That's why the name is like that. So basically, this algorithm is not complete as the A star. So it doesn't give you an optimal solution. So possibly the optimal solution would be something like this, but it did find a path. And quickly. It's not guaranteed to find a path, obviously, because it's probabilistic. But we say this algorithm is probabilistically complete because if you have the number of nodes reaching toward infinity, you would have a solution. You're guaranteed to have a solution if the number of nodes was infinity. So that's why we call it probabilistically complete. But it's not optimal. What can we do to make it optimal is the algorithm called RRT star. And that actually makes maybe a clever adjustment to this algorithm. So it selects a node somewhere. And instead of connecting this to only the closest node, it looks into a radius, or even something like this in this example, and looks at the costs. If connecting this node to this one gives you a better solution, it connects it to this one regardless of the distance within a certain tolerance. So this would give you something like this, and this node should have been actually maybe linked to this because the cost of going through this node is 3, but you could have done it in 2 steps. So this is the RRT star algorithm. There are also variants which you start at 2 ends. So you start populating the tree from the starting configuration, but you can start another tree at the goal configuration. So they expand toward each other. And these are all algorithms that we use to make this search better. And because these are short, you can sort out the action problem to traverse between these nodes, these configurations.
Do you end up using a combination of these things depending on the problem, or is the one that you sort of favour for everything?
So it depends on the problem. So for mobile robotics, for very simple applications, in the lectures as well, we do use the A star algorithm, which comes out of the box. For many purposes, that is sufficient. For manipulators, you do a combination of things. So we did talk about A star, which is classified under search-based algorithms. And these ones, RRT star, and other roadmap-based algorithms, they are classified under sampling-based algorithms. There are algorithms that are, for example, learning-based, which uses reinforcement learning. There are algorithms that are optimization-based, which looks at how you can optimize through a cost function or through certain criteria. And I think the state of the art is to use a combination of these. So for manipulators, we do generally use a combination of different methodologies, so hybrid approaches do hold. Sampling-based algorithms, there are many more than this. You can find implementations in the Open Motion Planning library. And after selecting maybe a feasible path, one approach is to use optimization-based techniques to make it really nicer, to fine-tune the final path. The probabilistically good one. If the space looks very much alike, then you're kind of in trouble, because this algorithm, which uses a Bayes filter, actually uses the similarities in space. So the robot always tries to find something